Hello, this is Dr. Strickland. In this video, we will investigate organometallic reagents involving lithium or magnesium. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, if you wanted to do this transformation, you take bromobenzene and turn it into ethylbenzene, think about the reactions that we know so far that are substitutions or eliminations. Can you use one of those reactions to do this transformation? And the answer is no. And the big deal is that this carbon right here is sp2 hybridized. I mean, this is clearly a substitution, but we can't do SN1 or SN2 at an sp2 hybridized carbon. It has to be an sp3. So the search was on for ways to do these kinds of reactions. And this is where organometallic reagents enter the picture. So we want to see the difference between when you have an electrophilic carbon versus a nucleophilic carbon. And carbon is electrophilic when it's attached to something that's more electronegative. A leaving group, more specifically a halogen leaving group, right? So chlorine, fluorine, bromine. So just put that like that to show that we're talking about halide ions being the leaving group here. So if we have a nucleophile, we know that it can attack this guy because it's an electrophilic carbon. It's less electronegative than what it's connected to. And so then this bond breaks and we get the product of the substitution. But if you have a situation where carbon is attached to something that's less electronegative, like a metal, then it's going to be nucleophilic because then the greater electronegativity is here rather than there. And so now you've got it sort of an opposite situation. And the products look like this. Okay. All right. So the ones that we're going to talk about involve some of the metals here. And so any organometallic compound has a carbon metal bond. And the greater the polarity of the carbon metal bond, the more reactive the organometallic compound will be as a nucleophile and a base. So we're talking about the difference in electronegativity between carbon and the particular metal. So this is lithium. So I'm going to go and snag the electronegativity of lithium to find out the difference in electronegativity between them. So I want you to pause the video and do these three and then come on back. All right, welcome back. So this is an absolute value. So you can use, you can put the bigger one first and the smaller one second or vice versa. And it doesn't make any difference at all. You get a positive difference. Magnesium here is 1.2. That gives us a difference of 1.3. Then we've got copper, which is over here at 1.8. Make that a little taller. 0.7. And then palladium is over here, 2.4. Which gives us a difference of 0.1. So you can see that the bonds are more polar in this direction. More polar carbon metal bond, which makes the carbon a better nucleophile and a stronger base. All right, so come on down here. So first we're going to talk about organometallic reagents, and then we'll talk about organometallic catalysts. And these reagents involve lithium or magnesium as the metal, And if you go back up here, you can see that these are the two metals that are involved in the most polar bonds. Okay, so these guys, more polar bond. Gives you a more reactive organometallic reagent. And it can act in two ways, as a nucleophile and as a base. All right, so let's see how that works with these two metals. If you want to make an organometallic reagent involving lithium or magnesium, then what you need is an alkyl halide of some sort, and then just the neutral metal. And so any kind of alkyl halide or vinylic halide or aryl halide will work. I've dealt with substitution and elimination reactions where mostly you had to have alkyl halides, but now it's opened up to include pretty much anyone you can think of. So, for example, here, this is the general reaction pattern involving lithium and an alkyl halide. And so you can see you need two equivalents of the lithium, and it forms two products. This is the one that we're primarily interested in, and this is just a side product. And over here with the magnesium, one equivalent, and there is no second product. All right, so I want you to pause the video and write out the structures of these four products from the general reaction pattern, and then come on back. All right, welcome back. So you can see that with organolithiums, the lithium takes the place of the halogen. So that makes that organolithium, and I'm going to just put this in parentheses because it's not going to be part of any reaction where this is used. If you had an aryl halide instead, this is just bromobenzene, it would make phenylithium. And again, because the halogen is the same, we get the same salt as a side product. Over here with Grignard reagents, instead of the metal taking the place of the halogen, it gets inserted between the carbon and the bromine, like this. And then finally, if we've got a vinylic halide, same sort of situation, where the insertion is going to happen right at the position where the halogen is. And you get something like that. Okay, so the one limitation on the alkyl halides that you can use to make these reagents is that you can't have any kind of an acidic functional group also in the molecule. So, this is just a simple alkyl halide, but a lot of compounds have more than one functional group in them. So if you had an alcohol, a thiol, an amine, an alkyne, or a carboxylic acid somewhere else in the structure, you couldn't make the Grignard reagent out of it because the corresponding deprotonation reaction would be faster. So just to illustrate that, I could make this, but then if it came into contact with water, say from your solvent, from your glassware, from your reagents, then you would get a deprotonation here of the water. And let's put that other hydrogen right there. And you get this as a side product. Okay, so you can't have a polyfunctional molecule that has any of these functional groups in it. You also can't have any water around your Grignard reaction of any kind because it will just undo your Grignard reagent in a heartbeat. So when you do a Grignard reaction in lab, Make sure that you have no water anywhere. Not in your solvent, not on your glassware, not contaminating your reagents. Okay, so that is the basic story on organometallic reagents involving lithium and magnesium. If you have any questions, please send them to me.